Right. So right-hand rule number 2. We're going to start with a quick review of right-hand rule number 1, for those of you that maybe forgot over the break. We're going to get you caught up, don't worry. So for those of you that don't remember, if you run a current through a wire, a magnetic field is actually produced around that wire. Now, right-hand rule 1 gives us some information about how that field looks. So, for example, if this is our wire right here, and the current is traveling to the top of the page, then the field lines that are generated around that are circles, and the direction of those field lines looks like that.
Why are they like that? Wouldn't they be like...
Now you do that using the rule. Now if you look, if this were our wire, yes, it's very funny that I'm on the screen. If this were our wire and see, the baby liked it. Whoever watches this recording later is going to wonder why they hear a baby in the background. Not anymore, apparently. So, if this is the wire and the current's traveling up, you use your right hand, not your left. Should be easy for you, Hennika. You grab onto the wire, and your thumb goes in the direction of current flow. So I said the current's flowing up, so therefore my thumb is pointing up. Now if you look at my fingers around, there we go, my fingers coil around the wire. That is how the field lines would look. They're circles around the wire. And at any point, I can take my finger and point. So if I'm below the wire here, and I placed a compass right here, because compasses are affected by magnetic fields, then the direction in which that compass would point is to the left. My left, your right. All right? If we rotate it around, if I placed a compass directly beside this wire, then the direction in which the field lines would be pointing is up. If I place the compass directly above the wire, then you keep rotating around, and the direction it's going to be pointing is your left. All right? And then I'm not going to twist my arm all the way around. If I placed a compass on this side of the wire, then again, grabbing it, it's going to be pointing down. Okay? So it's just a circle that goes around, and the direction is determined by which way the current's going. If we reverse the current, so instead of having the current go up, the current went down, then that reverses the direction of the field lines. So now the field lines go around this way, and it's actually the opposite of what we just saw. So another thing that may help some of you visualize this, we have here the field lines going around. Now, if the current's going towards the screen, wrap it with my right hand, and you can see that it is the blue arrows that represent the field lines. If the current's going away from the screen, my thumb's pointing the opposite way, then it's the red arrows. Okay? So that's right-hand rule 1.
Yay! Will you tell us if it's like going away?
So what happens if we loop that wire? Oh my goodness. This is just taking the field lines, and I've drawn them the same way. So it's going in front. So current's going this way. Field lines are going around, so it goes in behind here and out around the front. So right in the center here, on this side of the wire, the field lines would be pointing in which direction? Into the page or out of the page? Out of the page. Current's flowing from the right-hand side to the left-hand side. You can see the arrow there. So if I grabbed onto the wire right here with current flowing up, and this is using right-hand rule 1, current flowing up, then right at the center here, the field lines would be pointing out. If I move up to the top here, again, current's still flowing in the same direction. Field lines on the inside of my loop are going to be pointing same way, out of the page. And if I go all the way to the other side here, same way. So what happens if we have all these fields, all these different fields with the wire acting on in the same direction at the same point? Something. It increases the strength of the field. So what happens when we have all these fields interacting here? So these 3 points here, 1, 2, 3. If we loop it over and make it strong enough, they're all interacting and they're all acting in the same way. So you have an applied force from this magnetic field here. You have a force from this field here. You have a force from this field here. Now you have all 3 of them acting together and on the same point, and all in the same direction. So it makes the field stronger. So because they're all acting in the same direction, we get a stronger magnetic field. Well, what happens if I loop that wire over again? Maybe not twice as strong, but stronger, right? You have more fields, more magnetic field acting in the same direction, pushing in the same direction, you get a stronger field. So if we looped it over and over and over again, and they're all acting in the same direction, it's going to, don't copy this one down just yet because we're going to come back to it.
Wait, is the green thing the wire? Or
the green thing's the wire. The blue thing would be a solenoid or a magnetic material of some sort. But you don't, it's just something you put inside. It doesn't have to be there. You can actually just loop the wire, as I am right here. You can loop the wire like that and get the same effect. Putting the solenoid in or a magnetic material makes it the field significantly stronger. So this brings us to right-hand rule number 2. So the second right-hand rule helps us determine which end of this electromagnet is north. Or, if you know which end is north, it'll help you. You can use it to determine in which direction the current is flowing in the coiled wire. So it's a little different than right-hand rule 1. Fingers are the direction of current flow from positive to negative as it coils around. And your thumb represents the direction of the electromagnet in which there is a north pole. Well, I'll show you an example, okay? So the fingers, this is the third point here. Fingers are the direction of current flow from positive to negative as it coils around. Your thumb represents the direction in which the north pole is located on that particular electromagnet.
So your fingers are flowing towards the negative. And the reflecting.
Yes. I'll show you an example in 1 second. And adding a magnetic material into the loops of wire increases the strength of the magnetic field. So when we looked at this example here, we've got the wire wrapped around, the current's flowing from the right-hand side to the left-hand side. So you would start with your fingers. I like to start with one finger. Now, the way I've drawn this one here, it goes in front of the solenoid first. And that's the other reason why we put the solenoid in there, because it makes it easier to distinguish which way it's wrapped. And the way it's wrapped or coiled does make a difference. So we start by going in front, and then we would wrap around. If you try and do it the other way, your fingers don't really wrap around this way. Okay? So you start, the current's flowing this way, wraps around. So can you guess which end of this electromagnet is north?
That way.
Yeah. Now I want to stress to you right now, every year I get at least a dozen students that make this mistake with right-hand rule 2 and the electromagnets in general. Just because the current is flowing out of this end does not mean that this end is going to be north. If we coiled this the other way around, it would actually reverse the poles. But every year I get at least a dozen students that say, oh, well, the current's coming out over here, this has got to be north.
So
Or they'll say, oh, the current's going in here, this has to be north. And it depends on that first example that they see. So what I want to do right now is...
even bother mentioning the topics of wait, Mr. Hello.
Hold on. No, it does affect the answer, but the rule is not where the current is coming out. The rule is the direction in which the current is flowing and how it is coiled around.
But if my thumb's always north, then it's always going to be flowing this way.
Okay, hold on. I'll show you an example where it's not, okay? Aaron, did you have a quick question? All right.
Oh,
Shh. We're recording, by the way. So don't confuse current flow and north and south pole. You must interpret the question to determine the correct answer. Alexis?
thank you.
And then here I've outlined the differences between right-hand rule 1 and right-hand rule 2. So here is an example of an exam question. I actually pulled this off of last year's exam. And since there's only so many ways I can ask, how does the field look in this direction or at this point, I would probably copy this one down. So here's another exam question. Oh, by the way, for the previous question here, the answer was at point P, the field lines are going to point out of the page, just for those that are watching. Yeah, but I didn't tell the recording that. It'd be kind of annoying to watch the whole recording and then not get the answer. Okay, so this one is another exam style question. I left the multiple choice answers there, so you can work on that. So the North Pole would be at location A, because it wraps in front of the solenoid first.